Hey there, welcome to Kung Fu Physics, where we are working our way through physics GRE problems on the practice exams, one problem at a time. Today's problem is off of the 2001 exam, 2001 problem number 91. Looks something like this. So if you have it printed off at home, get it out. Follow along. 91. Otherwise referred to as silly dumb algebra problem masquerading as a physics problem. That's kind of what I see this one as. It's really pretty easy as long as you don't, as long as you're accurate. So, but you can certainly do this problem in under 2 minutes in the way that I'm going to lay out. I just looked at some of the postings for solutions. There's some interesting thoughts on some of the shortcuts that you might use to this. Honestly, I don't know that they save that much time. I think this can be pretty much done in a little under 2 minutes. Just cranking it out. So let's go ahead and do this. Number 91. Brief look at the answers. You got lots of mr squared stuff in there. 1/2 mr squared in answer A, mr squared in answer D. These should be reminiscent of moments of inertia of something. They will all have the same units, of course. All of the answers. I may be able to answer or eliminate either A or D, for example, because I may remember that those are specifically moments of inertia of some specific types of objects. So that may or may not help me. So that would be a very quick scan that some of those thoughts might race through my head right before I start the actual problem. Don't take too much time scanning the answers, of course. Brief look at the diagram and then we're off. Number 91. The cylinder shown above with mass m and radius r has a radially dependent density. The cylinder starts from rest and rolls without slipping down an inclined plane of height h. At the bottom of the plane, its translational speed is hgh over 7 quantities to the 1/2. Which of the following is the rotational inertia of the cylinder? Don't let rotational inertia of the cylinder throw you too much. I mean, that it is suggestive, that way of calling it is suggestive of it's the equivalent of mass for rotational motion. So you're looking for I. Otherwise, you could call it the moment of inertia, I guess, about the center. They don't explicitly say that about what points, but they're saying the rotational inertia of the cylinder. We could start playing around with the answers and say, well, maybe it's not answer A or D, and we may be justified in eliminating a couple of those at this point. But it's not worth dwelling on it too much. So we would go ahead and start this problem that, as I say, will ultimately just pan out as being an algebra problem. I think the quickest way to solve it is conservation of energy. As I usually do, I just like to set the energy initial equal to the energy final. We have no friction or anything like that that's pulling energy out that we would have to consider in there. So it should be fairly straightforward. Conceptually, we should be seeing this in our head as all of the energy is potential energy at the top, and then this thing starts down, and the potential energy gets converted to forms of kinetic energy once it reaches the bottom. So the first little stumbling block is the potential energy. What do we put as the initial energy? mg and h. Can I go ahead and just throw in big H there? You should have a quick moment of pause there, glancing back at the diagram and just thinking that through. Because to the center mass of that cylinder is not H. It's H plus the radius, plus R. However, think about the actual distance that the thing drops. When it gets down to the bottom and it's on the ground, as described in the problem, as it's down at the bottom, the center of mass is still going to be located a distance r above the ground. So the distance the center of mass actually dropped is indeed h, and we would go ahead and do that. So by all means, be paranoid, but don't waste time for the sake of paranoia on these problems. So quickly you would say I'm going to use h there, and then I want my kinetic energy, my translational energy, 1/2 mv squared plus 1/2 I omega squared. So this is my kinetic energy in translation and rotation, right? We don't have an omega. There's nothing that gave us an omega, so we need to get that. And we get that by noting quickly, as it does in several of these physics GRE practice problems, the thing rolls without slipping. What that means to us is we have the following relation. V equals omega times r. So when something is slipping, that's what our translational velocity of the center of mass is going to turn out being. And conceptually, hopefully that makes sense to you. There's no sense to try and explain, what that is as the thing turns. It's related to how big the radius is of the, if you think of it as like a wheel, and the wheel is moving that much. So the more the wheel turns and the bigger the radius is, it depends on how far that thing is going to go. So blah blah blah, you guys know this already, and I'm poking away, wasting time. So omega equals v over r, omega squared equals v squared over r squared. That's the substitution that we're going to make here that's important. And so on we go. You know what? I'll go ahead and plug that right in here. I'm going to erase omega squared and put in v squared over r squared. Now, the v squared is the v is 8gh divided by 7, all that under a square root. So to square it, it's just 8gh over 7. So anywhere I see a v squared, I'm going to plug in an 8gh over 7. And as I said, it's just a yucky algebra problem. I'm going to move this r squared over here, I over r squared, and then 8gh over 7. And the more accurate you can be, the better. If you can be accurate and quick about this, then all the better. I like to cross things out. That's kind of the way I do it to save time. So if I get GH's on both sides of the equation, I will cross them out. I get 2 and 7 on the bottom on both terms on this side, so it's 14. We have 14m equals 8m plus I over r squared, 8i over r squared. I subtract the 8m, makes sense to me the way that I've done it here. 8i over r squared, blah blah blah. And so we get 6/8 mr squared is what I equals. And if you were quick about that, and I wasn't, talking as much as I was actually doing it, I think you could work through that pretty quick. So I would be scrambling to look at the answers here at this point, and I would even maybe rewrite it for myself when I didn't see the answer there. I would just make sure, okay, divide by 2, 3/4 mr squared. Make sure I did it right. You would hate to do all of this and waste all this time and make a stupid little algebra mistake at the end and mess it up. Alright, so 3/4 mr squared, is that one of our answers? Indeed it is. Answer B is the one we would be going with, 3/4 mr squared. So as I said, pretty easy physics problem, but imperative that you are accurate in your work on these. Look at some of the other solutions. There are some interesting shortcuts that I saw that involve substituting, and you can of course substitute in a value. You could substitute in like 1 for G or H, or some things like that, and that may help you. I still think that just going through it this way, like I said, without all the commentary, I could knock this out in a couple of minutes or less. So I feel pretty good about the way that I've laid it out there. So there we go. That was number 91 off of the 2001 exam. And study hard. Catch you next time.